So now in this video, we are going to combine a couple of topics that I covered in a recent video. So here's an integrated circuit where you see these random jumpers. Those are inputs right there. That's the supply voltage, positive supply, and negative supply voltage there. The LED, the long lead, the anode is down lower. The short lead, the cathode, is up higher just because you got to put it in the right way for it to light up. So right now the output's high, and current's flowing through the LED that way to the negative supply. And when I turn the trim pot high, now the output's low, the LED is off. And we're not too concerned about the basics of this circuitry right there. Instead, we're kind of interested in the output voltage. So integrated circuits commonly are not great at powering loads. Even a light load like the LED. The outputs of each one of these NOT gates, they are not connected to anything. We can leave them floating. You don't want to leave the inputs floating. Again, topics from earlier videos. But right now the output is high. It's given the most voltage that it can give, but the LED is drawing current. And there you can see, actually, that was the voltage across the resistor. There we go. That's the total voltage. And it's a little awkward wiring here. But this is the voltage across the resistor and the LED. So it's basically the voltage of the output to ground right there. Well, it is high. Of course, if it's low, it's ground on both sides. We'll have 0 volts and the LED is off, as you can see right there. Now we go high. We'll look at that voltage again right there. We'll get rid of the LED. Now, when we measure the voltage, all we're going to see is the output. Even though I'm going to the resistor, it doesn't go to anything, which is basically the full supply voltage. As we see there, it's falling a little bit shy of 5 volts. So now, if for some reason that was a problem, we can't lose that much voltage or something, or we have a load that needs even more power, down here we have an N Channel enhancement mode MOSFET. So I used this transistor in the last video. Now I got to swivel the LED around, and we're going cathode to the drain up there. And then I know it's kind of hard to tell, but the resistor and the LED are directly connected. So right now the transistor, it's in an on state, but it's actually floating. So we're going to move this jumper, and the LED may have stayed on. I didn't mean to pop this out, but we're going to where the resistor is. So this is the output. Once I get a good grip on the jumper, that's the output again of one of the NOT gates right there, the same one we were using before. And now we're using it to turn the transistor on. So when the output is high, the transistor will be on, and also when it's floating, it could be in either state. Be aware of that. This doesn't depend on current to be on or off. It depends on the voltage. And so if when I remove my finger, whatever voltage I set there, it kind of holds. So I'm picking up stray signals. So again, we can turn it off the same way. High input, low output, it's off. That's how the N Channel enhancement mode MOSFET works. And now the high output is turning the transistor on, which turns the LED on there. It looks like the LED is brighter. I turned my lamp down a little bit. It auto adjusts light levels. This might beep. I try not to leave it just sitting there too long. So yeah, back to voltage. What we're interested in, we can zoom in. We got space there. So the jumper is going to the gate. That controls how well it conducts here. And we will take a voltage measurement across the load now, because that's what matters with how much current's going. So there you can see, again, we're not getting that perfect supply voltage. The transistor is not conducting perfectly, but you can see we got a lot more voltage across the load than we did before. We can also look at how much voltage is across the transistor right there, a little bit. But the vast majority is across the load now, a lot more than we're not losing near as much as we were from the output there. So these particular integrated circuits, this is the 74HC, so it's the high-speed CMOS version. 14 means there's 6 or hex NOT gates in there. So the high-speed CMOS version of these integrated circuits, they can provide, a significant amount of power, but as we saw when we're lighting the LED directly with the 220 ohm resistor, we were losing some amount of voltage. That may be a problem, it may not. But the solution to that problem is to just use a transistor. Use that output to turn a transistor on or off. The MOSFET, as I said before, just looks at voltage. Current doesn't flow through the gate. And we could also use a resistor, doesn't matter. It will build up that voltage and either conduct or be off if the output's low right there. Low enough voltage will turn it off. And these make good switches, these MOSFETs. Very easy, turn on or off. And after that point, it just does its thing. Doesn't need current like the bipolar junction transistor does, which, a really sensitive, or a really weak, I should say, voltage, might not even be able to turn a bipolar junction transistor on and off fully, whereas it will easily do so with the MOSFET because it doesn't need any current, just a little bit shuffles while you're turning it on or off, and a very, very small, practically nothing leaks through. Always something's going to leak through just a tiny bit. You never get perfectly no conduction, but you get very, very close. It's, for all intents purposes, no conduction. So that was the main point of this video. I covered these two components recently, so I'm not going to go into a ton of details about them, and but I think I mentioned everything that you kind of need to know to understand what's going on here. I rushed through it though. I am aware of that. But in case, hopefully you still enjoyed. The main thing was we were looking at how much voltage we were losing from the output there. Because when I do these integrated circuits, I mentioned for serious loads, you'll probably be switching transistors instead of trying to power the load from the output. But I use LEDs to indicate when the output's high or low. So the LED is a load. You can power LEDs, but it may not even be the option that you want to use right from the output. You might want, even with LEDs, these low power LEDs, to switch with the transistor. So I mentioned that in the videos, but a demonstration I would hope helps even more. And if you're not aware of trim pot, we got the full supply voltage across the trim pot. We get a fraction of the voltage. So there's a Schmidt trigger effect. We go a bit above the halfway point, we have a high input, and we go a bit below the halfway point, now we have a low input. But since it's a NOT gate, the output is the opposite. So low in equals high out. I can just put the LED here. You can see the resistor is coming from the output and then through the LED going to ground. I had to swivel it around right there. So high output, low over there. But this trim pot is low. When we got high, now it's ground there, and it's ground on that side. There's no voltage difference. The LED is not going to light up. Sometimes I have a blue LED wired to also light up when it's low. The blue LED lights up pretty good when it's low. I think this output may go to ground a lot better than the positive supply. But I'm not going to set all that up right now. But also the blue LED doesn't need as much current. I use a higher value resistor, so the less current you demand from the output, the less it's going to throw off its voltage as well. When we have no current there, we're getting this full supply voltage, maybe losing just like hundredths of a volt. But we looked at that in an earlier video. In fact, we'll look at that now. So I jumped ahead and rewired the LED. So right now you can see that's the more positive side right there. The trim pot has a higher input, so we know the output's low. It's connected to ground as good as it can be. And we're going to set the multimeter to measure voltage right here. And again, we're going to go to the output and see how close we are to a 0 volt. So I'm touching the LED. I'm trying to miss everything out. And there you can see it's actually how much current. So we can either sink or source current with the output right there. Right now the output is sinking current. That is more positive there, headed to more negative. So it's flowing in the opposite way, but you can see we're building up about the same voltage. That was the voltage at the output. We can check the voltage across the load. So I'll put the black probe there and the red probe across the resistor. So now I'm measuring the voltage across the resistor and the LED. And there you can see it's about the same right there as it was when current was flowing the other way. So 555 timers, their output does connect to ground a lot better than the positive supply. These CMOS, it looks like it just depends on how much current you're asking of it.